Swayam Prabha. Digital India. Educated India.
Welcome back. We are going to start this lecture by solving the practice problem where we ended our last lecture. So the problem goes like this: the water flows up a tapered pipe as shown in the figure below. Find the magnitude and direction of the deflection H of the differential mercury manometer corresponding to a discharge of 120 liters per second. The friction in the pipe can be completely neglected. The reason of neglecting the friction completely is so that we are able to apply Bernoulli's equation. Okay, fine. So if we say that S be the relative density of mercury, so if we have relative density of mercury S, we can relate all the densities to water using this relative density. Okay, so for the manometer here, considering the elevation this section as the datum, we can write the we can write the Bernoulli's equation as P1 by gamma plus X plus H, all right, here plus H is equal to P2 by gamma plus 0.8, what is 0.8? This is 0.8 plus X plus S into H, because this is the mercury, all right, understood? All right, this is from fluid statics. What we are doing is we are equating the pressures here. So P1 by gamma plus X, you see this here, start from here, we go down X plus we go H down again. Okay, so this is this, starting at 1. Now that will be equal to, if we are able to find P2, so P2 by gamma plus 0.8, that is because this is 80 centimeters, plus X plus, because this is pressure but the mercury is there, no water, so instead of H we write SH, and this is how we get this equation. Okay, all right. So we can write P1 by gamma minus P2 by gamma minus 0.8, because X gets cancelled, plus is equal to S minus 1 into H. So this will become, S is 13.6, that becomes 12.6 into H, all right. So by continuity criterion, Q is going to be, you see, pi by 4 area A1 V1. So V1 we know, okay, so V1 is the velocity at this section, area, because this is 30 centimeters in diameter, okay. So pi d square by 4 into V1 is Q1. So D1, so pi by 4, okay, into V2. So here this is A2 and this is V2, this is A1, this is V1, alright. So, V1 from this method, because Q is already given. What is the Q already given? 120 liters per second. So, we can find V1 and therefore, we also can find out V2. Now, by Bernoulli's equation for points 1 and 2, P1 by gamma plus V1 square by 2g plus Z1 is equal to P2 by gamma plus V2 square by 2g plus Z2. So, P1 by gamma minus P2 by gamma plus 0 minus 0.8, if you calculate Z1 and Z2, is equal to V2 square minus V1 square by 2g. This is going to come to 2.034, alright. So, P1 minus P2 by gamma minus 0.8 is also equal to 12.6 H, and that is also equal to 2.2034. Therefore, H can be found out as 2.2034 divided by 12.6, and that gives H is equal to 17.5 centimeters. Alright. So, we have used continuity equation, we have used Bernoulli's equation, we have also used fluid statics, alright, and using all those three we have found out the value of H, here, okay, great. So, this completes our Bernoulli's equation. However, we are going to continue with the final topic of the basics of fluid mechanics, that is called fluid dynamics. So, we have read about fluid statics, we have read about elementary fluid dynamics, that is Bernoulli's equation, we have read about fluid kinematics, we have read about properties of fluid, and this we are going to see so that we are able to solve the momentum equations, for example, in the fluid flow. This, I mean, these all topics are very briefly taught because you have already done in a lot of detail in your fluid mechanics second year course. So, to start fluid dynamics, one of the most important theorems that generally is not taught in fluid mechanics is a Reynolds transport theorem. So, what we are going to do? We are going to derive this Reynolds transport theorem in a little bit more detail. So, all physical laws are stated in terms of various physical parameters. Okay. So, if B represents any of these parameters can be velocity, acceleration, mass, temperature, momentum, anything, etc. So, what it says is, let B represent any of these fluid parameter, capital B, okay, and small b represent the amount of that parameter per unit mass, that is capital B is equal to m into B, right, where m is the mass of the portion of the fluid of interest, right. B will be 1 if capital B is equal to m, right. So, B is the amount of that parameter per unit mass, alright. Good. The parameter B, capital B, is termed as extensive property, and the parameter small b is termed as intensive property, because it is the parameter per unit mass. The value of capital B is directly proportional to the amount of mass being considered, whereas the value of a small b is independent of the amount of mass, because by definition it is the amount of the parameter per unit mass, a small b, alright. The amount of an extensive property that the system possesses at a given instant, B sys, So, B sys is the amount of the extensive property that a system will have at any given instant. And how that can be found out? It can be determined by adding up the amount associated with each fluid particle in the system. It is very simple. So, B system can be calculated by summing up different B's, B, capital B of each particle. If for an infinitesimal fluid particles of size delta V and mass rho delta V, this summation takes the form of an integration over all the particles in the system. So, if we start considering the fluid particle, small particle of size delta V, and we tend the limit to 0, this B sys will be integration of all the particles of the system. So, capital B system is summation of Bi rho I. So, it is a summation of the mass, right? Correct. So, this can be written as rho B dA. You see, dA or dV, whatever, sorry, not dA, it is rho B dV, alright, because that is the capital B. Capital B was small m into small b, alright. So, m is mass is rho into dV and multiplied by B. This is the B system, this is the integration. Okay, I will remove this. I hope this is getting clear to you a little. The limits of the integration cover the entire system. So, it can be a moving volume as well. So, I am taking this so as not to give you difficult questions in the exam or the test, but this is to make you feel and appreciate how these momentum equations that we are going to see in the fluid dynamics, how do they have their origin. So, Reynolds transport theorem is very, very important in that aspect. So, so for doing that, we have used the fact that the amount of B in a fluid particle of mass rho delta V is given in terms of B by, this is what we have assumed in getting this delta B is equal to B rho delta V, alright. So, most of the laws governing fluid motion involve the time rate of change of an extensive property of a fluid system. Okay. The rate at which the momentum of a system changes with time, for example, or the rate at which the mass of the system changes with time, and so on. Thus, we often encounter terms such as dB sys dt. So, not only B system is important, but that is the summation of, so B summation B sys was integral system rho B dV, right. So, this is important, but not only this, the derivative of this B sys is also important, because at many times we require that mass, rate of change of mass or rate of change of momentum. So, those things are required. So, that is why it is important to know these derivatives. To formulate the laws into a control volume approach, we must obtain an expression for time rate of change of an extensive property within a control volume BCV and not within a system. So, we have to obtain the rate of change of extensive property in a control volume. Okay. And so, until now what we have been doing is we have written this extensive property in terms of a system, but to be able to obtain laws and formulate laws, we should be writing that not in terms of system, but in terms of control volume. Okay. So, the same thing we can write d dt of BCV is the differential of, so this from system goes to control volume. the same equation. Okay. So now this is the prelude to, but now we are going to derive the Reynolds transport theorem. We consider the control volume to be that stationary volume within the pipe or duct between section 1 and 2. Okay. So this figure have been taken from Monsoon, Young and Okishi, yeah. So you can refer to that book for the derivation of Reynolds transport theorem as well. So again repeating, we consider the control volume to be that stationary volume within the pipe or duct between section 1 and 2. This is section 1, this is section 2, or in this figure section 1, section 2. The system that we consider is that fluid occupying the control volume at some initial time t. Okay, right. So this blue line here, this line, I'll just take the laser pointer. So this blue line is the fixed control surface at time t. However, after time delta t, that is at t is equal to t plus delta t, our system boundary has moved from here to here. All right. So we have divided it into 3 regions, 1, control volume 1, 2. All right. So at short time later, at time t plus delta t, the system has moved slightly to the right. You see here, as we talked about, this has moved from here to here. The fluid particles that coincided with section 2 of the control surface at time t have moved a distance. So the distance that has moved is v2 into delta t. You see here, if this had a velocity v2, this would have moved by v2 delta t, and this would have moved by v1 delta t. Okay, where v2 is the velocity of the fluid as it passes section 2. Similarly, the fluid initially at section 1 has moved a distance delta L1 is equal to v1 delta t, where v1 is the fluid velocity at section 1. This I have already shown you in the previous figure. Okay. If b is an extensive parameter of the system, then the value of it for the system at time t is b system is equal to b control volume, right. Since the system and the fluid within the control volume coincide at this time, its value at time t plus delta t is, see again I am repeating, here the system and the fluid within the control volume both are coinciding at the beginning, right. So b system is equal to b control volume, that is true. Now if we want to find out the value of b system or b control volume at t plus delta t, so b system at t plus delta t will be b of control volume t plus delta t minus b of 1 at t plus delta t plus b2 at t plus delta t. Okay. So now taking you back, what actually is b1 and b2, right. So you see, this was 1, this was 2, all right, because this has moved right now, but earlier it was a part of b system. So this is simply we write b Cv t plus delta t minus this has moved, but this has already proceeded forward. So it has come into the system of b system. Thus the change in the amount of b in the system in time interval delta t divided by this time interval is given by, if b is an extensive parameter of the system, we can write delta b system by del t. So the change will be equal to B system T plus delta T minus B system T divided by delta T, right. This is very standard, and we have already written B system at T and B system at T plus delta T. This is T plus delta T, and the so B system at T plus delta T is coming from here, right, minus B system at T. This remains same, okay. By using the fact that at initial time t we have B system T is equal to B control volume T, okay, alright. This is what we seen in the last slide, correct. We can rearrange this. How? We see in the next slide. So, delta B system by del T became B CV T plus delta T minus this one became this, and this is the one that is here in the next slide here, okay, minus B1 T plus delta T divided by delta T plus B2 T plus delta T divided by delta T. So, in the limit t tends to 0, the first term on the right hand side of equation is seen to be the time rate of change of amount of B within the control volume. So, this one, alright. So, limit B CV T plus delta T minus B CV at T by delta T, or it can be written as del B CV del T, or integral of this we have seen in the previous slide, alright. The third term on the right hand side of equation, so the third term on the right hand side of the equation represents the rate at which extensive parameter B flows from control volume, right, across the control surface. This can be seen from the fact that amount of B within region 2, the outflow region, is its amount per unit volume, rho B times the volume, that is delta V11 is equal to A2 into delta A2. Hence, B2 at T plus delta T can be written as rho 2 B2 multiplied by delta V2, okay, or in terms of it is called A2 V2 delta T. So, where B2 and rho 2 are the constant values of B and rho across section 2. Thus, the rate at which the property flows from the control volume B out is given by B out is given as limit delta T tends to 0 B2 at T plus delta T divided by delta T, or we can simply write rho 2 A2 V2 B2, correct, simply the total mass that is flowing out of the cross section area 2. Similarly, there will be an inflow of B into the control volume in the section 1 during the time interval delta T, correct, and that will be equal to rho 1 B1 A1 V1 delta T, okay. So, now putting this all together, where B1 and rho 1 are the constant values of B and rho cross section 1, thus the rate at which the property flows is given by rho 1 A1 V1 B1. If we combine all the equations, we see that the relationship between the time rate of change of B for system and that for the control volume is given by capital D dt of B system is del T of B CV plus B out minus B in, alright, or del B system dt is equal to del B CV delta T plus rho 2 A2 V2 B2 minus rho 1 A1 B1. This is one equation that we obtain. Now, this equation, above equation, this is a very simplified version of the Reynolds transport theorem, and this we have derived from the scratch, the most basic thing. So now the next step is we have to find this for control volume and system for flow through an arbitrary fixed control volume. Okay, this is arbitrary. Alright, so now we will derive it for more general conditions. So this is the general condition. Okay, so this is inflow is happening in this, this is outflow area, and this is the original control volume. The fixed control surface and the system boundary at time t is equal to t, and system boundary at time t plus delta t. So we consider an extensive fluid property B and seek to determine how the rate of change of B associated with the system is related to the change of B within the control volume at any instant. Same procedure, but for the any arbitrary surface. Okay. So in general, the control volume may contain more than one inlet and one outlet. A typical pipe system, for example, can contain several inlets and outlets as shown in this figure, for example, can be more than that or even less than that, right. So we have to find a general equations. So this is the outflow portion of the control surface, this one here. This is cross sectional area out, this is delta A, this is the V velocity, and this is the normal surface, this is the velocity, okay, and this is the theta. Now in time delta t, this has progressed V delta t, right, and this length will be delta L. So this length that have progressed, okay, is delta Ln into delta A. All right. So a more clear figure, this is the one that gives a more clearer picture. This is normal to the, this is the velocity, and this makes an angle theta with the normal direction. Okay. So the component of delta L in normal direction is given as delta Ln. Okay. All right. The term B out represents the net flow rate of the property B from the control volume. See, its value can be thought of as arising from the addition of the contributions through each infinitesimal area element of size of the portion dA of the control surface dividing region 2 and control volume. This surface is noted as CS out. That is what we talked about, I was showing on the figure. So let us suppose in time delta t, the volume of fluid that passes across each element is given by delta Ln into delta A, where delta Ln is delta L cos theta in the previous figure is the height of the small volume of element, and theta is the rate at which B is carried out of the control volume across the small element, denoted is angle between the velocity vector and outward pointing normal to the surface n. So theta is the the angle between the velocity and the eta. Thus since delta L is equal to V delta t, the amount of property B carried across the element area delta A in the time interval delta t is given by simple same thing B rho V cos theta dt into delta A. Same, now instead of V it is V cos theta, okay, direction. The rate at which B is carried out of the control volume across the small element area delta A denoted by delta B out is, so delta B out is given by rho B delta A delta t or rho B V cos theta delta E delta A by delta t. All right. That is rho B V cos theta delta A. I will just. So this is the main this is the delta B out. The rate at which B is carried out of the is denoted by B out. So, by integrating over the entire outflow portion of the control surface, we obtain B out as integral of dB out as rho B. So, we substitute this rho B V cos theta delta A. The quantity V cos theta is the component of the velocity normal to the area element delta A. From the definition of the dot product, this can be written as V cos theta as V dot n. Hence, an alternate form of the outflow rate is rho B V dot n multiplied by delta A. In a similar fashion, by considering the inflow portion of the control surface, Cs in can be written as, because it was negative sign, rho B V dot n dA. Okay. So, for outflow region, just remember V dot n is greater than 0 and theta is between 90 degree and minus 90 to 90. So, for inflow region, the normal component of V is negative and for outflow region it is positive. So, V dot n is less than 0 and theta varies from 90 to 270. So, value of cos theta is therefore positive on the CV out proportion of the control surface and negative on the CV in portions. Over the remainder of the control surface, there is no inflow or outflow, leading to V is n is equal to 0 on those portion. On such portion, either V is equal to 0 or cos theta is equal to 0. Therefore, showing the cross section in. Therefore, the net flux of the parameter B across the entire control surface can be written as B out minus Bn is equal to Cs out rho B P dot n delta A. Almost the same expression, just the cross sections are different. Or we can also write over the entire cross section, because at other places this component is 0. There is only a contribution at outside and inside which can be taken care of from this expression. Okay, I will just delete this one. So, this is where the integration is over the entire control surface. By combining of equations, we obtain dB sys by dt is equal to del B CV del T plus control volume or control integration over a control surface rho B V dot n is equal to dA. This can be written in a slightly different form by using, so that BCV is equal to rho B dV. We can also write this in this form, del T of control volume. So, what we did, we just this one we wrote in this format. Okay. So, now this is the general form of Reynolds transport theorem for a fixed non-deforming control volume. Okay. So, now if we move from a system to a control volume, so okay, we are going to cover this sometimes later. I think this is time now, and the next step would be moving on from this Reynolds transport theorem. This is a generalized form. I hope you would have understood that. Just in case you haven't, you please look at your books. I have tried to derive it in the most simplest form. So, in the next class, what we are going to see, we are going to apply this Reynolds transport theorem to fluid dynamics, where this property B, can either be mass or momentum, and then we are going to work. This can be anything because we have derived it for a general system. So, B sys can be anything. So, I think this is enough for today, and the lectures will conclude that. I hope to see you in the next class. Thank you so much.